Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Johan Alif bin Wan Ajaha, metric number 2017466056. My supervisor for FYP is Miss Nur Hashima alias. So today, I would like to present on my final year project presentation, which is my topic is smart nanofibers for membrane distillation. So for table of contents, first is problem statement, second objective, third membrane distillation, and fourth is fabrication of electrospinning nanofiber. In recent years, industrial wastewater discharge and oil spills have caused great damage to water resources. Water pollution not only brings about imbalance in the ecological environment, but directly also affects human health. Therefore, there is an urgent need for scientists to develop effective wastewater purify technology to solve these significant issues. Some previously reported strategies such as adsorption, filtration, centrifugation, catalysis, biological treatment, and electro-coales have been widely applied in wastewater treatment, whereas high energy consumption, secondary pollution, and unrepeatable usage still seem to be inevitable. At the beginning of 21st century, nanotechnology becomes one of the most competitive research fields. It has been considered as the leading technology of the new industrial revolution. Nanofibers with high porosity, large specific surface area, and high size uniformity are expected to become effective wastewater treatment materials. Many approaches have been confirmed to prepare nanofibers. In particular, electrospinning is probably the most attractive technology for fabrication of nanofibers due to its simple and low cost. And now, more than 200 synthetic and natural polymers have been successfully electrospun into nanofibers membrane. And now for the problem statement. Progress on nanofibers development increased rapidly due to their highly porous structure, narrow pore size and distribution, specific surface area and compatibility with inorganics. Electrospinning has been introduced as one of the most efficient techniques for the fabrication of polymeric nanofibers due to its ability to fabricate nanostructure with unique properties such as a high surface area and porosity. The process and the operating parameters affect the nanofiber fabrication and the application of nanofibers in various fields such as sensors, tissue engineering, wound dressing, protective clothes, filtration, desalination, and distillation. Desalination of seawater using membrane distillation can be a practical approach to mitigate the freshwater's scarcity during drought season. Therefore, this study will focus on fabrication of nanofibers for membrane distillation application. Various desalination technologies are emerging to tackle the increasing water demand globally. The developments of new membrane materials and novel processes have shown that nanofiber can potentially applied in the desalination due to enhanced flux, lower operational pressure, and energy savings. Nanotechnology-based products such as nanoparticles and nanofibers have been introduced to enhance the properties and performance of the membrane derived from conventional polymeric membrane material and conventional phase inversion process. When mid-layer made up of electrospinning nanofibers membrane, higher per mid flux than conventional membranes were achieved. Based on the aforementioned research background and problem statements, the objective of this study are: first, to fabricate the nanofiber membrane using electrospinning technique for membrane distillation; second, to examine the physico-chemical properties of fabricated nanofiber membranes; and last, to evaluate the membrane separation performance of the membrane distillation. For the scope of work, first, fabricating nanofiber membrane using electrospinning technique; second, examining the physico-chemical and thermal properties of the fabricated nanofiber membrane using X-ray diffraction (XRD) Fourier transform infrared spectroscopy (FTIR), thermal gravimetric analyzer (TGA), and SEM. And third, evaluating the separation performance of the fabricated nanofiber membranes using benchtop filtration setup. And now we moving on to the membrane distillation. Membrane distillation is a thermally driven membrane separation process. In a typical membrane distillation, a vapor pressure is generated across the two sides of the hydrophobic porous membrane by circulating the hot feed and cold permeate. The vapor generated on the hot feed side pass through the membrane and condense on the cold side to produce the distillate. The vapor pressure difference increase with increase in temperature difference between the feed and the permeate. However, membrane distillation is considered a low temperature process typically operated below 80 Celsius. And as you can see on the figure, water vapor molecules in the hot feed are able to pass through the pores of the membrane, whereas the liquid feed is prevented from transporting through the membrane pores. This phenomenon is mainly because of the hydrophobic nature of the membrane distillation and its low surface energy. In membrane distillation process, it is important to keep the pore of the membrane dry to prevent the liquid feed to directly pass through the hydrophobic membrane. The membrane distillation process is divided into 4 configurations depending on the way the permeate side is processed. First, direct contact membrane distillation (DCMD). Second, sweeping gas membrane distillation (SGMD). Third is vacuum membrane distillation (VMD). And fourth is air gap membrane distillation (AGMD). For the first, direct contact membrane distillation, this is the simplest configuration in which the membrane is in direct contact with the cold water. The water vapor produced at the hot feed liquid membrane interface pass through the membrane pores condense in the cold liquid membrane interface at the permeate side. Despite the simplicity of this configuration, the conduction heat loss associated with this process is higher compared to other configuration. Due to high heat loss, DCMD has low thermal efficiency, which is defined as the fraction of heat energy used only for evaporation. In DCMD, different membrane modules can be used, such as hollow fiber or flat sheet under cross flow or longitudinal flow. It is best suited for applications such as desalination and concentration of aqueous solution. And second, for the air gap membrane distillation (AGMD), as the name suggests, an air gap is created between the membrane and a condensation surface, as shown in figure below. Because of air gap between the membrane and condensing surface, the heat loss is low and the configuration exhibit the highest energy efficiency, but the permeate flux obtained is generally low because of additional resistance offered to mass transfer by the air gap. By narrowing the air gap, this deficiency can be overcome to a certain extent, since in air gap MD, the permeate is not in direct contact with the membrane. There is no danger of membrane wetting at the permeate side. And third, for the sweep gas membrane distillation (SGMD), in SGMD, and third, for the sweep gas membrane distillation (SGMD), in SGMD, an inert gas is used as a carrier for the transportation of the produced vapor to the outside condenser. The schematic of SGMD is shown in figure below. It is particularly suitable for removing volatiles from an aqueous solution. Sweep gas in this configuration reduce the mass transfer resistance as compared to the air gap membrane distillation. However, it needs a separate condenser outside the module, which add additional cost to the SGMD configuration, and also a leak-proof gas system is required for this configuration. And last is vacuum membrane distillation (VMD). In this configuration, Vapors on the permit side is removed by applying the vacuum as illustrated below and condensed outside the module. The vacuum applied on the permit side is lower than the saturation pressure of volatile molecules to be separated from the feed solution. This configuration is useful when volatiles are being removed from an aqueous solution. Many approaches have been confirmed to prepare nanofibers, including drawing, electrospinning, template synthesis, phase separation, interfacial polymerization, and self-assembly. But electrospinning is probably the most attractive technology for fabrication of nanofibers due to its simple and low cost. The electrospinning process has been considered as a production of microfibers to nanofibers from polymer solution under high electric field at a atmospheric pressure and room temperature. Electrospinning device have two main setup, vertical and horizontal. Power supply, high voltage, screench, spinneret and collector electrode are considered the main three components of the electrospinning device. High voltage generates electric charge on polymer solution and this charge accumulate on its surface. These charges repel each other such that a critical electric field that they are able to overcome the solution surface tension and form a Taylor cone. A charged jet is ejected from the Taylor cone tip which is stretches further in the electric field. The jet finally convert to solid fibers because solvent evaporation. Stable jet obtained at the spinneret needle after that convert into unstable jet to form electrospoon fibers via simple techniques. When the applied electric field at its critical value, the charge repulsion force overcome the surface tension and jets erupt from the cone tip and transfer the tensile force to polymer and form bending instability of that polymer. Then jet travel from the cone apex to the collector with opposite charges, which have ability to attract the charged fibers. Solvent evaporated through jet traveling to leave dry fiber on the collector. High voltage power supply, syringe, and collector electrode can make typical electrospinning device which may be assembled in vertical or horizontal setup as shown below. Continuous nanofibers can be formed via electrospinning process of polymeric materials and there are several parameters determining the quality of electrospoon nanofibers. These parameters are either polymer properties, concentration, viscosity, surface tension, and conductivity, or processing parameters electric field, flow rate, needle tip to collector distance. And the conclusion for my presentation, first, the simplicity and versatility of the electrospinning technique has paved the way for the fabrication of nanofibers. Second, electrospoon nanofibers membrane have gained significant attention as one of the key solutions for upgrading and upscaling membrane distillation process for treating water and wastewater. And third, AGMD can be widely employed for most membrane distillation applications, particularly where energy availability is low. Okay, that's all from me. Thank you very much.